Hello everybody, I am Dolphikaris Mason, a senior mechanical engineering student at Arizona State University. This video is my project for heat transfers course with Dr. David Benson. Today I'm gonna introduce the concept of conduction, convection, energy balance, control volume, and control surface by solving a problem. But before we start solving the problem, I just want to mention a few things. First, heat transfer always occurs from hot to cold. And we have three modes of heat transfer, and they are conduction, convection, and radiation. For today, I'm not going to talk about radiation. Conduction is a transfer of heat or thermal energy by touching, and it occurs in solids. For the convection heat transfer, it occurs when we have a flow of a fluid, gas or liquid. Now let's talk about the problem. You can pause the video and read the problem. I'm gonna read the problem and then clarify some parts of it. So we have a thin electrical heating element provides a uniform heat flux to the outer surface of a duct through which air flows. The duct wall has a thickness of 10 millimeter and a thermal conductivity of 20 watt over meter times Kelvin. For part A, at a particular location, the air temperature is 30 Celsius and the convection heat transfer coefficient between the air and the inner surface of the duct is 100. What heat flux is required to maintain the inner surface of the duct at 85 Celsius? And for part B, we are asked for the conditions of part A, what is the temperature of the duct surface next to the heater? So we are asked to find the heat flux and the T naught, which is next to the heater, and we're giving the thickness, which is 10 millimeters, although it's written as L equals 10 millimeter. L in this case is the thickness, not the length. Some student thinks that L stands for the length, but it's not. It's the thickness. And we're giving the ambient air temperature and the heat transfer coefficient. So we have convection, obviously, because it's air, and as mentioned already, air is a fluid, so convection occurs. Also, for the duct wall, we're giving the thermal conductivity, and we also have insulation. So when we're given the K value, it just means that a conduction occurs between solids because the duct wall is a solid. And other than that, I don't think anything is confusing. Before we start solving for the problem, I just want to mention something that is confusing for many students, and it is about Q. We have three different Qs. The first one is Q by itself, and it's the heat rate, and it's in watt. The second Q is Q prime, and that is heat rate per unit length. So it's in watt per meter. And the very last Q, it's a Q double prime, and that is heat flux, and it's in watt per meter squared. So watt per area. So in this question, we are asked to find the heat flux. So we're gonna have to divide by the area. So let's start solving part A. We are asked to find the heat flux required to maintain the inner surface of the duct at 85 Celsius. So first we need to start drawing our control volume around what is interesting for us. Everything inside the dash line is the control volume, and the dash line is the control surface. For part A, we're asked to find the heat flux, so we are not going to take into account the insulation because we don't know nothing about it except the K, and we don't know T out. That's why we are not going to draw our control volume around that part. We are just gonna draw the control volume above it as shown in the green dash lines. So now we are going to have the energy balance equation, which is energy in minus energy out plus the energy that is generated, and all of this is equal to the energy stored. Now we need to have some assumptions in order to cancel some parts of the equation above. So the first assumption is steady state conditions. Since there is nothing about time is mentioned in the problem, we can assume it's a steady state problem. So nothing varies with time. There is no storage. So the right hand side term on the energy balance equation gonna be cancelled. And for our second assumption, we're gonna assume there is no internal generation. So the E-gen is going to be cancelled. So we will be left with energy in equals energy out. For our third assumption, as I mentioned already, we gonna neglect radiation for this problem. And the very last assumption is that we are going to have constant properties everywhere in the duct. The K, the thermal conductivity, is not gonna vary like in all the duct wall. Everywhere it's K is going to be the same. So as I mentioned, we are left with E entering is equal to E is going out, and we know that the entering part for the control volume is the heat flux. So Q now, notice that I just wrote Q, not Q double prime, is equal to Q convection. But we are not asked to find the Q naught because we won't be able to find the Q naught because we are not giving any dimensions in the problem. We don't know the length, we don't know the height, we don't know nothing about that except the thickness. So in order to get rid of that, to solve the dimension problem, we're gonna divide by area for both sides. So for the left hand side, it's gonna be Q over A. As I already mentioned, heat flux units are watt per meter squared. Area units is meter squared. So Q over A is Q double prime, which is the heat flux. And for the right hand side of the problem, of the equation, sorry, we're gonna have H delta T. Delta T is hot minus cold. The hot part in this part is the Ti minus T infinity, because Ti is 85, the hot, and the ambient air is cold, which is 30. So solving for heat flux, which equals to H Ti minus T infinity, we gonna be left with 5,500 watt per meter squared. Great. For the second part, we are asked to find the temperature of the surface next to the heater. So how can we do that? We can do that honestly in two different ways. By taking a control surface, a very tiny control surface in the bottom of the duct, or we also can take the control volume in the upper part of the duct. But for what I'm going to do is I'm going to do a control surface around the bottom surface. And I clarified how we can get to energy in equals energy out. But for this particular part, notice that what is entering is heat flux, same as part A. But what is going out of the control surface is the Q, the heat conduction heat transfer. As I mentioned at the beginning of the video, conduction occurs when we have solids, and the wall is made of a solid. That is why we have conduction in this part. So Q na is equal to Q conduction. Again, we're gonna have to divide by the area in order to get to the heat flux that we already solved for. So we're gonna divide both sides by A. We're gonna be left with the heat flux is equal to K over L. L stands for the thickness, not the length. We are giving the thickness, which equals delta T, again, hot minus cold. But in this case, the hot temperature is the T na, because it is closer to the heater. So it's absolutely going to be hotter. Minus T inner, which we already know it, and it's 85. So solving, and also notice that the thickness is 10 millimeters. We have to convert that to meters. That is why it's 0.01. Solving for the temperature, we get 87.5. So there is no big difference between the temperature that is very close to the heater and the other one, which is 85, because of the type of material. We have the thermal conductivity is equal to 20, which is very good. That's why there is no much variation. And thank you so much.